Today, I would like to go over CUDA programming. However, before I do that, the first thing we should probably go over is what a GPU is, which will give us a much better understanding of CUDA, since it utilizes the GPU's processing power in order to accomplish its tasks. So what is a GPU? GPU stands for Graphical Processing Unit, and it's the very heart of basically every computer that displays graphical interfaces. There are many uses for a GPU, however, the main uses involve displaying and rendering images, and other uses involving data simulations, database searches, that involve huge quantities of data. So what's the difference between a GPU and a CPU? Now, I'm sure a lot of you enjoy hardware specs, so I came up with two comparisons between the GeForce GTX 980, which is around the $500 price range, and the Intel i7 5930, which is also around the $500 price range. Notice the huge difference between the clock cores. The GPU is running at 1.2 gigahertz, while the CPU is running at 3 times that speed. However, once you get to the amount of threads the GPU can run, you quickly realize that it's far superior in that aspect, as each CUDA core can run 10 plus threads at once, while at most the CPU can do is 2 per core. So now that we have a decent understanding of what a GPU can do, let's move on to CUDA. CUDA stands for Compute Unified Device Architecture, and it is used to compute massive amounts of data using any type of NVIDIA GPU. This allows the user to utilize the GPU through programming languages like C and C++, which we all know. So now on to the example. For an example of how CUDA program can benefit the user, let's go over a simple computation using 3 vectors. So how would we add 2 vectors, A and B, to C for a huge data size? In the standard C++ way, we would just use a for loop to go through A and B and add it to C one by one n amounts of times depending on how long the vectors are. With the CUDA C libraries, it would turn the for loop into an actual function which you would call to do the computation. To do this, you would call the function and it will go through allocating each computation to a particular thread denoted by the allocation of a variable I that specifies the thread ID, block ID, and grid dimensions used to figure out which thread it should go to. So after that, we would like to go over a demo.
For our demonstration, I have 2 programs. One written in C++ that uses the standard libraries, the other also written in C++ but using the CUDA libraries. Both of these programs take 2 vectors, add them together, and store them into a 3rd vector. Open in front of me here I have the first program, the one that uses the standard libraries. It's actually quite a simple program. It has 3 vectors, vector A, vector B, and vector C, which are declared and allocated enough memory for 10 million elements each. After that's declared and allocated, we have a for loop here that initializes vector A and vector B to some values, and then vector C to 0. That's the vector that we're going to be storing our results into. The actual addition of the vectors is simple. It's just a for loop that adds vector A and vector B into vector C for all I elements. And then we have a clock function immediately before and after that for loop to measure how long it takes to add the 2 vectors together. I'll run this program, and I'll minimize the results for now. Next, I'll open the CUDA version of this program, which is actually quite similar, but there are some differences. First off, we do have to include the CUDA libraries, which allows us to run this on our GPU. We still have the same 3 vectors, vector A, vector B, and vector C, which we declare and allocate memory the same way as we did in the first program. We also initialize these vectors the same way as we did in the first program. There are 3 additional vectors, vector dA, dB, and dC, which are allocated some memory, but not this time on the actual local memory, but on the graphics card memory. These D's stand for device, which stands for the GPU. Once those are allocated, and we've initialized our first vectors, we can then copy our vector A and vector B into vector dA and vector dB on the graphics card memory. Once those are copied over, we then run our function called vector add, which has the same result of a for loop adding these vectors together, but instead does them in parallel. We still run the clock before and after that function to measure how long it takes to add them together. And then we also have a CUDA memcopy function after the vector addition is completed to retrieve our vector C from the graphics card memory. I'll run this program as well. And I'll pull up the first one. So the program on the right is the one that was executed on the CPU, the one on the left executed on the GPU. You'll notice both programs yield the same results, although the one on the GPU did run faster. Now, we didn't measure the time that it took to copy the memory over from the CPU to the GPU because it's 10 million elements, which takes quite a bit of time transferring over a thin PCIe bus. If we did measure the time it took to transfer all of that data, the GPU would actually take a little bit longer to execute. For small programs such as vector addition, it's not really worth trying to do this on a GPU in parallel. Utilizing the GPU for parallel execution comes more in handy when doing problems such as matrix multiplication or physics simulations, where the problems are much larger and the computations are much more intensive.